Lovely. Okay, so apart from setting the bar low for everyone else talking today, I'm going to be talking on a topic that came from the Goyder Institute Water Sensitive Urban Design Project, and there was a specific study within that which was assessing the impact of water sensitive urban design on the capacity of urban drainage systems. So what was this all about? It all came from a single, multifaceted problem. Essentially, we wanted to know what impact infill development has on flow rates during storm events and what water sensitive urban design can do to help that. So when we're talking about infill development, I've got an example on the slide here. Talking about the process of turning a single allotment in residential catchments, generally, in existing urban areas into multi-dwelling allotments. So the process is shown here. We've got an area of Glengarry in 1993 on the left-hand side, and the same area in 2007 on the right-hand side. So you can see people have knocked down a house and put up 3 or 4 houses in its place, which is a perfectly legal thing to do, and everyone needs a house to live in. So. Now in 2010, according to the 30-year plan for Greater Adelaide, half of development in Adelaide was infill development and half was greenfield development on the urban fringe, such as you see large land releases. However, by 2040, it's intended this is going to shift for 70% infill development and only 30% on the urban fringe. So there's going to be a lot more urban infill development occurring. And we know that this increases impervious areas in existing catchments. This is increasing the runoff volume and the peak flow rate, the maximum flow rate that occurs for a stormwater event. And based on interviews with local government, we understand infill is already placing stress on existing drainage systems. So that's where the whole project essentially came from. And just a quick illustration of the impact that infill development has. So this was a theoretical catchment we did at the very beginning of the study, but I think it's illustrative of the problem. The blue line in this chart indicates the catchment response to a stormwater event before infill development. So you've got the hydrograph essentially, the flow rate reaching about 0.38 or something. Put a little bit of infill development on that catchment and you've got a much higher peak flow rate and a lot more runoff coming off the catchment. So the problem we're looking at here, just to reiterate, is what impact does it have on a real catchment, and can water sensitive urban design be used to maintain this pre-infill scenario? So can it keep the blue line blue as infill development progresses? We're not the first to look at this. Several studies have tried to examine the impact of this. The outcomes of studies vary. Some will say water sensitive urban design is effective, some say it's not, and some say it can help with peak flows, and some say it doesn't really have that much of an impact. These studies tend to have a variety of assumptions. Some of them are realistic, some of them are a bit fanciful. And the modelling in these studies is in particular often an issue because they'll use design storm events. If you're not familiar with a design storm event, you don't need to know, it's very unexciting. But it's essentially a single storm event. And the problem with that is illustrated on this slide here. So, as I said, the design storm event will simulate a single stormwater event, and the opposite of that is a continuous simulation where you simulate a whole bunch of events, a real-time series. So you take 10 years of rainfall data and run it as a model or a design program. So the problem with the design storm approach is if you were to take, this is a rainfall time series from Adelaide over a few days, I forget how long. I can't back calculate the minutes in the top of my head. But on the right-hand side there, you've got a 5-year event occurring. If I was to use that 5-year event to design a system, I would have to assume how much water is in rainwater tanks or in the soil of the catchment before the event occurs. If you use a continuous simulation, you capture all that interceding rainfall, which is actually 10 millimetres, which is enough to fill up rainwater tanks in some cases. So what we did in this study, which was different to previous studies, probably one of the key outcomes, was we actually developed an approach to use a continuous simulation to look at the performance of water sensitive urban design systems in urban catchments. So in our case, a bit of background, we used 19 years of rainfall data on calibrated models. We used 19 years because that was the longest period of continuous data we could find in the Adelaide Plains that was reasonable without any awful things happening. So I'll take you through an example of what we did to a catchment, and hopefully that'll make a little bit more sense when I start presenting the results and where they're derived from. So first we produced EPA SWIM-based models of urban catchments, because that model is about the only one that can cope with continuous simulation and all the systems we wanted to simulate. We used 2 urban catchments, and I've got the example here of Frederick Street in the city of Marion, the Frederick Street catchment. These were selected, by the way, because we had data with which we could calibrate a model on. So we didn't just invent catchments and hope that they were working. These models have been calibrated to real data. And we also did another catchment, which I won't be talking about today, which was the paddocks in the city of Salisbury. So step 2, we ran these models, which were very hard to pull them together. But once we actually finally got them together and calibrated, which is probably what's driven me insane for the past 18 months, once we got them working, we ran various scenarios. So this is the base scenario, the calibrated scenario, and then some theoretical scenarios. So overlying infill development and putting water-sensitive urban design features throughout the catchments to see what do they do. Now, when we run the model, we end up with a long hydrograph. From that, it's pretty easy to get a mean annual runoff value from that. It actually tells you that. The model will tell us that. The hard thing is to characterise peak flow rates and flooding in the catchment, which is where we employed a thing called partial series analysis. Now, I won't go into great detail on this. The process for that is spelled out in Australian Rainfall and Runoff. It's a hydrological handbook for Australia. But basically, the largest flow events from this chart, and you can see it in the same charts in the left-hand side of this slide. I can use the mouse, can't I? You pull the largest events out and you rank them, you plot them in a fanciful way, and you can determine the average recurrence interval of events occurring in that hydrograph. And finally, we extracted the frequency with which flooding occurs throughout the catchment. So in urban areas, flooding can be expected to start on a road adjacent to an undercapacity drain. That's generally where flooding will start to occur. So we determine the acceptable flood volume at critical points in the catchment where there's a drain that's going to be under capacity. And these are generally sag points, so where water's coming from both sides. And looking at this diagram on the right-hand side, essentially we wanted to preserve one lane of dry traffic. So if flooding occurred which was going to prevent one lane of dry traffic occurring at the critical point of the catchment, we consider that a flood event. It might only wet someone's feet or it might spill over into someone's house. We didn't do two-dimensional modelling, it was all one-dimensional, so we had to make an assumption on what's a flood and what's not. And that was our definition of what's unacceptable. And that's again based on accepted standards in Australian Rainfall and Runoff. So following this, the first thing to look at was what is the impact of infill on these real catchments. So the scenarios we looked at, and this is for the Frederick Street case, was the 1993 case, which is what we had calibrated data for. At the time there was 555 homes and a directly connected impervious area of 30%-ish. Then the next case was 2013, where we knew there were 632 homes and a directly connected impervious area of 35%, and we had to project flow based on our modelling. We had no monitoring for that stage. And then we flipped that out to 2040, which is the limit of the 30-year plan for Greater Adelaide. Based on the amount of homes that were subdivided in the previous 20 years, we took that forward to 2040 and had 781 homes and roughly 40% directly connected impervious area if people are going to keep paving the way they do. So what does infill development do to a catchment? It's not much of a surprise. Overall, it increased the runoff volume, the peak flow rates and the frequency of flooding that occurs in the catchment. So we found that flooding occurs on roughly a 2.6-year ARI peak flow. So the 2.6-year ARI peak flow will cause a flood to occur. So you might say the existing capacity of the system is 2.6 years. So every 2.6 years there'll be a flood occurring in that catchment, statistically speaking. Now the chart at the top here shows how you get two relationships in the partial series. Anyone who's interested in partial series might find this interesting. If you're not, have a nap. You'll see a bend here in the partial series. So normally a partial series, you'd typically expect it to have a linear relationship. Now the split in the linear relationships here occurs when the catchment starts flooding and you start having a system operating under a bit of pressure. And so that's why you get two relationships happening in the partial series. And for flooding, the flood frequency increased from roughly every 2.6 years when it was in 1993. And we projected about every 2.2 years due to infill development by 2013 and about every 1.7 years by 2040. So you're getting a lot more. The direct outcome of that would be possibly impacts on people who live nearby the flooding point, but possibly also a lot more complaints coming into councils for nuisance flooding occurring. Now, the key thing, which most people are probably more interested in, is can water-sensitive urban design actually help with this problem? So we examined water-sensitive urban design in terms of 3 particular systems. There was retention tanks, which I would consider as rainwater tanks or infiltration systems, systems that hold water back and don't put it to the stormwater system. It either goes into the ground or down your toilet or wherever. Then there was detention tanks, and these are slow-release systems which will generally put it out to the street and into the conventional stormwater system, but it does it a lot slower than if you just let it rush straight out. And we looked at street-scale rain gardens. We did a single scenario of those. I should also note that when I'm talking water-sensitive urban design in this study, I'm generally talking about the storage of these systems. So all of the extra functions of these systems are not generally considered. I'm just purely talking about the storage. And so just to stress, retention systems hold the water back. It goes somewhere else other than the stormwater system. Detention systems let it go slowly into the stormwater system. So there was over 60 cases for retention and over 60 cases for detention. And this reflects the number of different combinations that you could have throughout the catchment. So just going through those quickly, you've got 1, 5 and 10 kilolitre tank sizes connected to 100 metres squared of roof. That's about the maximum you can expect a rainwater tank or a detention tank to be connected to. And fitting them on new homes or every home in the catchment. So that would be like reflecting a policy decision, which was if you're going to build a new home in this catchment, you have to have a tank. Or on the every home case, it would probably have to be done via the local council funding a retrofitting to every home. That's what that's trying to capture, which one's going to be more effective. And the demand or the emptying times of these tanks was based on realistic values. I guess I defined what was realistic, but it was based on literature and what you'd expect emptying times for these tanks to be. Now the results were a bit of a mixed bag. So if we're talking retention tanks only here, and so for a retention tank, picture a rainwater tank is probably the easiest thing to think of. They don't really work if you only put them on new homes. They have an impact, so we can see here that the peak flow in 1993 from for the 1 year ARI event was 0.82 metres cubed a second. It had gone up to over 1 in 2040. So the 1 kilolitre, 5 kilolitre and the 10 kilolitre tanks had reduced the peak flow because they're intercepting some water, but it didn't restore it to the 1993 levels. However, if you chuck it on every house in the catchment, you can see it has a better impact. So I'm just comparing the new homes case for a 5 kilolitre tank here. Same aim, you're trying to reduce that 1.04 down to 0.82. If it's on every home, it works. If it's not on every home, it doesn't. So you really need a lot more tanks and a lot more impervious area connected to these systems to get them working. And finally, looking at the impacts on flooding. When 5 kilolitre tanks were applied to all homes, again, same result. If you're trying to restore flooding to its previous value, this chart is a bit hard to understand outside the context of the report. But I guess key thing to focus on is you want to bring this line down to this line. And by installing tanks on every home, you've brought the flooding frequency down below to what it originally was in 1993. And then detention. Now, the results for detention, I'll probably skim over them because we're a bit pressed for time. Just the main thing you need to know is the detention operated pretty much the same as retention in this case. Now, it's also worth noting that it may not be the case if the catchment was a lot bigger or a lot smaller, because you do have some funny things happening where detention systems can cause a lag in hydrographs. But for this catchment, for the catchment at this scale, detention operated pretty much the same as retention, had the same sort of results. On new homes, it doesn't have enough impact to preserve your peak flow rates, but on every home in the catchment, if it was a retrofit, the entire catchment, you're going to restore peak flow rates and even make them even better, depending on how big the hole in the tank is. Now, finally, bioretention systems. What could bioretention systems do for us? Now, bioretention systems were simulated pretty much as just a storage on the top of the street that's going to take some water, hold it, let it through the filter media and out a pipe at the base. So these systems did not infiltrate, and they were based on rain gardens that are currently being rolled out in Mile End. So there's plenty of debates you can have about whether these systems should infiltrate or not, depending on the underlying soils and what the road engineer at the you have to deal with at council is willing to do. What impact did they have? We found that they were effective to preserve flows in 1993 to 2013, but they were overwhelmed by 2040. Now that could be a function of, as I say, this is the design of these systems. If you were to increase the storage size on these things, so they operate more like an in-street detention system or a municipal detention system, you might improve their performance. Or if you had more of them, or if you had some alteration to the design so they hold more water back and let it go slower. These are the sort of functions we didn't really get a chance to go further into, but we've showed that they have promise, basically. So in conclusion, the main outcome from the entire process was we developed and assessed the effectiveness of water-sensitive urban design without assuming antecedent conditions by using continuous simulation. Water-sensitive urban design can assist with peak flow and flooding, but it must be applied broadly across the catchment to capture flows from large impervious areas. And detention and retention produced similar outcomes at this scale. We also found that if you're going to use on-site storage, about 5 kilolitres was about the best based on our assumptions. So if you're going up to the 10 kilolitre size tank, you don't really get much extra benefit. That's based on the connectivity that you can get to these systems. So if you had a much larger contributing area and a much larger use, you might have a different relationship. And some recommendations that we got from the project. First of all, field monitoring would be good to verify the modelling outcomes. All the impacts of infill have been based on modelling in this project. We are doing some work to verify that now, thankfully, in the same catchment. We also think it's wise to explore the impact of less distributed storage systems, such as municipal storages. So is there an option to have a rainwater tank on everyone's house? But what if it was possible, if there was some sort of municipal storage? So would it be more efficient, would it be more effective to have a one storage at the end of the street or one storage at the end of a cluster of streets? It would also be good to investigate the impact of these scenarios on smaller and larger catchments to see that the effect is still valid. Obviously, as a catchment gets larger, the impact of detained flows might change the resulting flow rate in particular. We also showed that storages on every home had the best impact, but is it best, as I say, is it best to put in more systems or connect more impervious area to existing systems? And what's cheaper? Probably the bottom line of all of this. Is it cheaper to upgrade the pipe system in response to infill development throughout residential streets? Or is it in fact cheaper to buy everyone a rainwater tank and have it installed? I'm not a civil estimator, so I haven't done that work, unfortunately. But that's a query we threw up as part of the project. This was the team that worked on the Water Sensitive Urban Design project, and thanks also to the City of Marion and City of Salisbury, who gave us a lot of information. And there's a report available if anyone's got sleeping difficulties.